only thing casually I think take her out. I knew what the show was. Yeah, I was really bad.
Yeah, it's the phone. I think you have a that was like some rust. He was playing rust.
Okay, good morning everyone. Good morning. So I'm going to complete the last part of the fin chapter, and then we'll move on to transient conduction. That's more better. All right. So for fins, we're going to look at two design criteria that establishes whether using a fin is actually a waste of time or if it is actually a beneficial thing. Okay? And they're called as the fin efficiency and the fin effectiveness. So design criteria. For fins. And I won't be solving a problem on these because if you know the formula, it is just plug and chug. But I want to show you the basic concept of what these things are. Okay? The first thing is fin efficiency. Eta F, okay, that's the label for fin efficiency, and it's defined as the following. Okay, so eta F is the heat loss rate from the selected fin. Okay, so if you're using a fin that is infinitely long, or if you're using a fin that is adiabatic at its tip, or if you're using a fin which is exposed to ambient conditions at its tip, or perhaps the temperature at the tip of the fin is prescribed. These are all the selections that are available to us. Okay? And we know how to calculate the heat loss rate. This is essentially the heat conducted into the base of the fin. Divided by the heat loss rate of an ideal fin, which requires some explanation. So I'm going to talk about an ideal fin first. So ideal fin. If you look at a fin, typically, right? This is the wall portion. I have the fin portion. At the base of the fin, the temperature is T suffix B. So here, x is equal to 0, x is equal to L. The temperature is T suffix B. An ideal fin is a fin where the temperature gradient along the length of the fin is 0. Which means that each and every point on the fin is at the same temperature as the base of the fin. And why is this a good thing? Is because the largest temperature that is occurring on the fin is at its base, since it's a cooling fin. And so if the temperature all around the length of the fin is equal to the base temperature, then I'm going to have the maximum cooling effect from using this particular fin, which is the convective heat transfer rate, H times A times the base temperature minus the ambient temperature. So if ambient is T infinity and so on. So an ideal fin is a fin where the temperature gradient along its length is 0. Which implies that each and every point on the fin is at the base temperature. And this behooves that the thermal conductivity of this fin has to be infinite. That also requires some explanation. So, ideal fin, thermal conductivity is infinitely large. The reason for that is the following. If I look at Q conduction, this is minus K. And if I look at the conductive flux, minus K times d theta by dx. Now the conductive flux is a finite quantity. Okay, that's not infinitely large. So if the conductive flux is a finite quantity, I cannot have an infinite amount of heat flux transferring through the length of the fin. That's impossible, physically speaking, right? So if the conductive flux is a finite quantity, and if the temperature gradient is 0 for an ideal fin, then the thermal conductivity has to be as large as possible so that the product of these two remains a finite number. Once again, last time, this is a finite quantity. For an ideal fin, the temperature gradient is essentially 0 all through the length of the fin. So for this number to be finite, I have to take a number that is really, really small, approaching 0, and I have to multiply it by a number that is really, really large, which approaches infinity, so that I end up getting a finite quantity. Okay? So that's the reasoning for the thermal conductivity being infinite. And so typically for a fin, you want the thermal conductivity to be as large as you can. You want to select a material whose thermal conductivity is very large so that the temperature gradient along the length of the fin is reduced, so that you have the maximum cooling effect, and so that the temperature at each and every point in the fin is approaching the base temperature. Okay? So if that is the case, then I'm going to write Q loss for an ideal fin is H times the surface area that is available for heat transfer times the temperature difference at any point in the fin. At any point in the fin, the temperature is the base temperature. This is the heat loss rate for an ideal fin. If I look at the heat loss rate for an actual fin, okay, let me select an infinitely long fin because it's the easiest of the lot. This is a selected fin. Q loss. For such a fin, we have derived this expression before. This is equal to capital M, where capital M is defined as the following concoction of parameters: theta B, H P, Kf, thermal conductivity of the selected fin, area of cross section of the selected fin, the perimeter of the selected fin, the heat transfer coefficient on the ambient surroundings. Theta B is Tb minus T infinity. So if I expand this out, so I'm selecting this fin, so Q loss, fin infinitely long, is Tb, T infinity, Hp, Kf AC to the power 1 by 2. Okay? So I have the ideal fin, which I would like to have, but I'm constrained by material properties which restrict the thermal conductivity from becoming infinitely large. I cannot come up with a material of that sort. If I did, I wouldn't be here. And I have this infinitely long fin, okay, which is the fin that I typically select. Let's see what the efficiency is going to be. Okay, so this is for an infinitely long situation. I just divide one by the other. So take the bottom one. This is Tb minus T infinity. Hp Kf AC divided by H times the surface area, remember, TB minus T. I can cancel off the TB minus T infinity on the bottom. And the top, I have a factor of h and h to the power half in the numerator, h in the denominator. I can simplify this, and I also note, let's say that we have a situation where the surface area is essentially the perimeter times the length. So this is the case where I have a straight rectangular fin. Take the surface area, which is nothing but the perimeter, multiplied by the length. Okay, so surface area is P times L, which is for a straight fin. Infinitely long, so the tip is essentially insulated, so I'm not including the surface area available at the tip for the convection heat transfer. Okay? So this is just the surface area besides the tip. If you are looking at a real situation, then you'll have to use what is called as a corrected length. Your textbook goes over that, we're not going to use that. A corrected length essentially takes care of the fact that in real fins, the tip need not be insulated, so you have to include that surface area as well for convective heat transfer. We're not doing that. Okay? So if I take care of this and I do the substitutions, then E to F infinitely long will end up being the following. So if I do the substitutions, this is H P Kf AC by to the power 1 by 2 H times, then this is going to be P times the length L, H in the denominator, P in the denominator, H to the power half, P to the power half. So if I cancel off some of these terms, I end up getting Kf AC HP to the power 1 by 2 times 1 by L. Can anybody tell me what those terms in the brackets with the square root 1 by 2 represent?
Square root of one.
Little one squared.
1 over little m.
1 over.
Okay, so this is 1 over little m, and this is essentially 1 times ml, which absolutely tells you if I am actually literally thinking of a fin that is infinitely long, then that is a losing proposition, because the efficiency is going to drop down to 0. So we cannot, and we do not obviously want a fin that is really so large that its efficiency is gone. We operate under the criterion that for an infinitely large fin, the product of m times L should be greater than or equal to 2.6, and that is sufficient. Okay? So this tells us that the efficiency drops as the length increases. So eta f infinitely long goes down as L increases. Okay. And I'm going to give you a couple of quiz problems, in-class quiz, which you will complete and upload by Friday this week. Okay? And I've written down the questions, but I want to talk about one more thing. So this is about fin efficiency. Normally, if your fin is less than 90% efficient, then don't use a fin. Most fins that are used for practical purposes have to be greater than 90% efficiency to warrant the additional cost, warrant the additional space requirements that entail the presence of a fin. Okay? So typically, this is a number greater than or equal to 90%. Okay. Second design parameter is called the fin effectiveness. This is the Greek letter epsilon, suffix f. And to understand this, I'm going to draw a figure, okay? And essentially epsilon is the ratio of these two figures, but not literally. In the first figure, I'm going to draw a fin. So here's my wall. So I'm going to say that the cross-sectional area of this fin is circular. So this is almost like a cylindrical fin here. Okay. So this is a wall with a fin on it. This is divided by the same wall without the fin but with a small base area shown. So this shaded area is the base area of the fin, or area of cross section of the fin essentially, or area of cross section. Now I'm going to draw the same wall. The protrusion is no longer there, but I'm still going to look at the same shaded portion, A suffix C. And the basic idea is the following. First of all, what's the temperature at the bottom figure where I'm shading the area? That has to be the temperature of the base of the fin. Right? So this is temperature T suffix B. In the figure on the top, the temperature at the base is T suffix B, but along the length of the fin, the temperature changes. Okay? So this is going to be some TB. This is T as a function of X. This is not an ideal fin, this is a real fin. What this figure tells you is that, okay, hey, if I don't use a fin, and if I capture the heat loss rate coming through this area, Q loss coming from this area, and if I compare this with the heat loss rate during the presence of a fin, which is essentially, all of these guys, what do you think should be the situation? If I want to actually use a fin, if I compare the heat loss rate coming through this area here, not the entire wall, just the small area here, dinky little fellow, and if I compare the heat loss rate coming through this protrusion, which one should be larger so that I can actually use a fin? The one on the top has to be larger, right? Obviously. Otherwise, what's the point in having a fin? It's just an ornament. And so from that perspective, I compare these two values, and that tells me the effectiveness of the fin, which is a number that has to be at least larger than 2, typically. Okay, these are industry numbers, not something that I cooked up. Epsilon F. And you've got to do both. You've got to look at the efficiency of the fin, which has to be around about 90% for a reasonable fin. You have to look at the effectiveness of the fin. Okay, efficiency is great, so what? Is it effective? If its effectiveness is less than 1 and efficiency is 90%, I'm just wasting my money. Okay? So this is going to be Q loss from the fin divided by Q loss from the area of cross section. If I calculate the two, and I'm going to do this for an infinitely long fin once again, to say infinitely long. Q loss we already wrote down. Is just capital M, which is 3b minus t infinity. HPKF AC to the power 1 by 2. Then Q loss AC is essentially just convective heat transfer coming from this little cross-sectional area AC, okay, which is exposed to the ambient conditions. And so that's going to be H times the cross-sectional area times the temperature difference between the base and the ambient. Okay, so this is going to be H AC TB minus T. Does this make sense to everybody? This is very practical, right? I mean, what's the use of a fin? It has to cool things. If I'm using a fin and the cooling efficiency I'm getting is like 20% and the effectiveness is 0.05, then I'm essentially increasing my space adding some extra components which increases the weight, and this is an absolute waste of my time. So I want to redesign this and see, okay, are these parameters coming to be satisfactory? If they are, then it's worth it. Okay? So if I take the ratio of these two, epsilon f infinitely long is going to be Tb minus T infinity, H3 KFAC YHAC those two creatures cancel. And you can do the same thing for an adiabatic fin, which is what you're going to do in your quiz. And I'll write that one down once I'm done with this. You can do this for a situation where the fin is open to ambient conversation. You can do this for a fin where the ambient, the tip temperature is specified. So multiple scenarios. You can do this with the problem we looked at last time as well. You can calculate the effectiveness and see if it is cooling on both sides or is it just a waste of our time. Okay? Now I'm going to take these parameters. I have h in the numerator to the power half, h in the denominator, ac to the power half, ac in the denominator. So epsilon f is going to end up being this combination of parameters kf, then I'm going to have perimeter, and then h ac to the power 1 by 2. This is not little m. We just looked at what was little m there. Okay, so this is some other weird combination. I'm not interested in giving it a name. But I'm interested in looking at the parameters that influence the effectiveness. First thing. To increase the effectiveness, what should I do? I should increase the thermal conductivity of the fin. Because K is a parameter right there, starkly sitting in the numerator. So epsilon f increases. If K fin increases, this is one reason for having a very high thermal conductivity. And the added benefit of that is also that the temperature gradients are reduced. Second, this is more of a geometric consideration. If I take the ratio of P by AC, which is the perimeter by the area of cross section, which gives you some kind of a characteristic length feature, I want to keep this ratio as large as possible so that the effectiveness is high. So keep it as large as possible. And if I do that, the effectiveness increases. And the consequence of this is most fins, which are really effective, are going to be either small, thin pins. If you look at a pin, the area of cross section is really small, so the ratio of the perimeter to area of cross section is actually a high value. Or if you look at very, very thin plates, if you take an IC chip, you're going to see small, thin slices present there, which are acting as fins, and that's because this ratio is maximized. Okay? So that's another added consideration. The third thing, which we don't control but we could perhaps, play around with the convection coefficient. I can't change it, but I can do some things. So H should be low, which implies effectiveness is high. So when you use fins for cooling, the question typically is, do you place the fin on the fluid side, the liquid side, or on the gas side? So I have an engine. I want to place some fins on it. Do I place it on the side where I'm sending in cooling fluid, liquid, or am I placing it on the gas side? The reason you want to place it on the gas side is because the convective heat transfer coefficient for gases is lesser than for liquids. And if that is the case, your effectiveness is gone. Okay? And another thing, if you're using forced convection with fins, that's not a good idea, because if I'm using forced convection, H is larger than in the situation for free convection or natural convection. So which is why you don't want to have a big blower sitting and then, blowing air across your fins. That is just going to increase H, which will decrease your effectiveness. And so two considerations that come from here. So place fins on side of low H, typically the side which has the gas, has the ambient fluid, and use free convection to get low H value. Free convection meaning that the process of convection, the process of that convective heat transfer takes place due to buoyancy considerations, okay, due to density variations from the temperature. There is no external agent that is blowing air across this board. Okay? Alright, now for your quiz question, I'll just write the question down here. Okay? This is, I believe, in class quiz 3. The same way that we have done everything, you got to obtain the efficiency and effectiveness, both of these, for a fin with an adiabatic tip. Obtain these two for a fin with an adiabatic tip. Things that do not change. The denominator in the efficiency, effectiveness does not change whatever fin you do select. Okay, so that's going to be the exact same thing that we have this denominator for the effectiveness for any kind of a fin that you select. The other thing, if I look at efficiency considerations, I have an ideal fin. Once again, the denominator there does not change. The only thing that changes is the numerator on both the situations. It's a small tweak from an infinitely long fin. Okay. All right, I'm going to move on to the last part of conductive heat transfer, perhaps the most interesting because time plays a role in it. Yes, question.
Sorry, I had a quick question regarding when you said use free convection to get lower H value. Why then, like for instance, like cooling like a CPU chip or something, and they have a fan pulling air through the heat sink?
Right, so that's not only the fin, right? You also have the heat sink which has to be cooled.
Okay.
Right.
Okay, so the fins shouldn't have anything blowing on them, but you're
Right,
pulling air
but the
from
heat sink itself has to pull through.
Okay.
Yeah, absolutely. Right. So I guess you've got to be careful on what type of applications these things are more desirable. All right. The last part of conduction, before we move to this list of radiation. Radiation is very interesting, don't get me wrong. Transient conduction, which is also equally interesting. And I'm going to do something that typically I don't do in this heat transfer class. I'm also going to look at unsteady, one-dimensional conductive heat transfer. That is, we're going to solve a partial differential equation. Or we're going to partially solve a partial differential equation. Okay? You'll see that when we cross the bridge. So, transient or unsteady conduction. You may have come across this in system dynamics. I'm not sure to what depth and extent, but we will spend some time on it, at least a couple of lectures. Okay? So first things first, there are two things that I want to tackle here. One is called a zero-dimensional conduction. Zero dimension means that temperature is just a function of time. And 1D unsteady conduction. Temperature is a function of one of the spatial variables and time. 2D is two spatial variables, 3D is the entire works, which is very difficult to solve. You use finite element or boundary element methods for that. Okay? So let's start with 0D. And why I'm looking at 1D unsteady as well is that I want to come up with a criterion that says, okay, hey, if certain conditions are satisfied, then I can say that this 1D unsteady conduction can be modeled as a zero-dimensional unsteady conduction so that spatial effects are ignorable. You may have come across this criterion as the Biot number criterion, and they would have just plugged in the value and told you it has to be less than 0.1. You will see why it has to be less than 0.1. Okay? Alright, let's get down a journey here. What's the idea of 0D unsteady conduction? What's the practical application? You have roller bearings. Inside the roller bearings you have the rollers. You want to take those roller bearings, they undergo heat treatment and so on, and then you take them and you dump them in a cold bath. The process of annealing, relieving stresses. That is an example of a zero-dimensional transient conduction problem because the rollers are at a very high temperature, the bath is at a lower temperature, the rollers are small enough that the temperature distribution within is uniform, and so after some time they just cool down, and this is called as convective cooling. You can have the exact opposite scenario. I have a very cold steel ball, drop it into a bathtub that is very, very hot, and after a certain amount of time, exponential increase in the temperature takes place, reaches steady state temperature, which is the temperature of the bathtub. That is called convective heating. So this is an example of a zero-dimensional conductive heat transfer. Where is it practically used in thermocouples? If you look at the junction of a thermocouple, the tip of a thermocouple, it's a sphere. You take it into the air, it reads the temperature immediately. That's an example of zero-dimensional conductive heat transfer because there are no gradients within the steel ball, the tip of the thermocouple. Okay? Alright, so I'm going to draw a figure, some arbitrary body in a tub of ambient fluid. Okay? We're going to assume the following. So assume the temperature gradients within this body is 0. So this is a fluid bath. Temperature within the body is 0, which means that the temperature is more or less uniform throughout the body. And I also want to talk about one application, but this is a trigger warning. This is an application in the mortuaries or the morgues. And I completely understand if you want to leave. Okay. So typically, the job of a mortician or a forensic expert is to estimate the time of the person's death, the time of the deceased person. And that can be done using the problem of transient zero-dimensional conduction heat transfer. And this is because the human body, the greatest machine ever, right, is more or less at a constant core temperature of 37 degrees Celsius or whatever Fahrenheit or Kelvin that you want to talk about. The core temperature is more or less constant. And so by knowing what the temperature of the person is at the time of the person passing away, you can come up with a zero-dimensional transient conduction model which will tell you what is the time that this person has passed away. Okay? So that's something that people use as a back of the envelope calculation. Typically, if you're a forensic expert and detectives and so on, they use it. Okay? All right. So now we're going to go back to our problem. So temperature gradients are 0. So the temperature of the body is uniform. I'm going to call it as T. As a function of time, we're going to assume unsteady, obviously. No heat generation because that is just a constant that is plugged in. Who cares about it? It's not a big deal to include heat generation. Okay. When I talk about heat generation, an example of heat generation in transient systems is small concrete blocks. Concrete has actually the setting of concrete is a process that releases a lot of heat as an exothermic reaction taking place within the concrete block. And that's the presence of heat generation there. And if you have a small block of concrete and on a sunny day, you can calculate the steady state temperature using these kinds of techniques that we talk about. Okay? But we'll assume that to be 0 for us. And 0 dimension, unsteady. Temperature here is T infinity. and the convective heat transfer coefficient is h. First law. Okay, we always start with the first law. E dot stored, E dot in, E dot out, E dot generated. Let me assume that the temperature initially of this body is T naught. Okay, so this temperature T at 0 is some T naught, and let me assume that T naught is less than T infinity, just for fun. Okay, so another assumption. Which means that after some time, after a sufficient finite amount of time, the temperature of the block is going to be equal to the temperature of the ambient fluid. Okay. Alright, so here I'm going to cancel off this. If I draw a control volume, a control surface around this body here, all I'm saying is that there is going to be some convective heat transfer into the body. Right? There is E dot in, there is no E dot out. E dot in coming from all sides along the surface area. So E dot out is 0. And if I write E dot stored, which we have written as the rate of change of the stored thermal energy, this is mass times specific heat capacity, dT by dt. E dot n, heat transfer from the ambient onto the body. One of you told me that in your practice, whatever midterm exam formula sheet, my convection formula is wrong. It's not wrong. I did not specifically tell you what the direction of heat transfer is. That is up to you, and that is up to the application. If the fluid is hotter than the body, heat comes from the fluid to the body. If the body is hotter than the fluid, vice versa. Okay? So E dot n is going to be H times A, surface area, temperature difference, T of T, right, is lesser. So you see that this is the situation. Does this make sense to everybody? Yes.
So normally would the E dot stored be a partial derivative?
E dot stored would normally be a partial derivative if there was a temperature gradient present within. Now there is no gradient present. Right. Absolutely. So if I look at a problem of 1D unsteady conduction, that's going to be PD. Alright, and I'm going to do a change of variables exactly like what we did for fins. I'm going to say theta of T is T minus T infinity, and the initial condition is essentially what we have in this problem. Theta at T is equal to T naught, not 0, let's say T naught, more general, is theta naught, which is T naught minus T infinity. So this is a first order ordinary differential equation with an initial condition. Fairly straightforward. I'm going to do the following though. Do the change of variables. M is rho times volume. Okay. So I'm going to do that substitution here. So I'm going to have rho times volume. And then I'm going to bring the H times AS onto the left hand side. Divide through by the denominator. Instead of dt by dt, I'm going to have d theta by dt, change of variables, same as we did for fins, and this is equal to theta with the negative sign. That's a piece of cake from system dynamics typically. Okay, first order ODE, or if I rewrite it, I'm going to have the following. Yes, sir.
What's happening to the C?
That's a good question. I swallowed it. Next. Okay, so if I rearrange this, I have the following. So rho C. Watch this. The ratio of volume by the surface area, I'm going to call it as a characteristic length L suffix C. Okay. So I'm going to say that volume by the surface area is LC. Characteristic length. So this is going to be rho C, LC by H, d theta by dt plus theta is equal to 0. System dynamics question, what do you call this quantity? as the first order time constant. The fundamental characteristic of a first order system is one variable which is a time constant. If the time constant is fast, the response is nimble. If the time constant is small, the response of the system is sluggish. Second order system, you have two characteristic variables, natural frequency and damping ratio. We will not come across that, of course. So I have this, I have the initial condition, theta naught at t is equal to t naught, and then I can solve this. I'm not going to go through the procedure of solving this. I want to talk about more important things. I will of course post the procedure of solving this in my notes. Okay? So if you solve, you're going to end up with the following solution. So solution theta by theta naught is e to the power, and I'm going to call that character there rho cv by or rho clc by h as tau. So this is going to be minus t minus t naught by tau, where tau is rho c lc by h. Let's unpack its units. Okay, let's make sure that this is indeed a time constant. It has units of seconds. Density kg per meter cube. Specific heat capacity joules per kg Kelvin. LC characteristic length, that's a meter. H is watts per meter square Kelvin. Okay, and so that's going to be, so H is watts per meter square Kelvin. What is watt? Watt is joules per second. So this is going to be joules per second. Meter square Kelvin. So meter square second Kelvin divided by joules. Kilogram cancels. Kelvin, go for a walk. Meter cube is gone. Joules are gone. I'm left with seconds. Everything works out beautifully. And in seconds. Question. Suppose the fluid was colder and the initial temperature of the body was hotter, would the solution be different? Would the ODE end up being different? Nothing should change. The only thing that changes is initial condition. Okay, so if you are cooling a hot body, it's going to start off at the higher temperature and exponentially come to steady state at the temperature of the ambient. If you are heating up a cold body, starts initially at a lower temperature and exponentially climbs to steady state. Okay? But before I go ahead and do those things, let's play around with this tau creature. So look at this. T minus T naught by tau. Okay, I'm going to look at that quantity. So this is the solution. I'm going to look at that creature there. So this is T minus T naught times 1 by tau, which is h by all of those things there. H by rho c LC. I'm going to multiply the top and the bottom by LC. I'm going to multiply the top and the bottom by the thermal conductivity. And I'm going to group these things in a nice way. Okay? So we did not do anything earth shattering. Everything remained the same. But I'm now going to club them together in the following manner. Take these guys, combine them together as one single parameter. So this is going to be H LC by K. And the rest of them is T minus T naught K by rho C LC square. Anybody know the name of this quantity here from system dynamics? When you did thermal systems in system, I hope you did that. But if you did that, what are the criterion that you used? Frequency in thermal systems? You could do frequency analysis in thermal systems, but I'm not interested in that. What is the criterion that you use is the Biot criterion. Okay, so this first number is called as a Biot number. Okay. So we're going to say Bi, Biot number, which is H LC by K. Watch this. Once again, a manipulation. 1 by I'm taking the same Biot number and writing it in the following manner. Can you tell me what this first quantity is called? Or convection. So this second quantity here has to be conduction, because I'm looking at thermal conductivity. So this is the ratio of the thermal resistance to conduction divided by the ratio of thermal resistance to convection. And you would have typically come across in system dynamics that the Biot number has to be really, really small, which means that there is no thermal resistance to conduction, approximately 0, which means that the temperature gradient is essentially 0. If there is no resistance to conduction, there is no gradient within the body. And that's where the number, Biot number being small, comes into play, but we are not at there. We have to look at what the physical dimensions are and those things. But keep this in mind. And the second creature, this quantity, I'm not sure if you guys remember this, if all of you remember this, but when we started talking about conductive heat transfer, the ratio of K by rho C was called as the thermal diffusivity, alpha. Okay? So that second quantity in the parenthesis is called as a Fourier number. Named after, obviously, a good friend Fourier, is alpha times T minus T naught by LC square, which also begs some manipulation. Okay, so the Fourier number is representative of the fact as to the rate of heat propagation through the body. If the Fourier number is very high, then this approximately means that your system thermal constant, time constant, is very small. Because you see that 1 by tau is proportional to the Fourier number. If the Fourier number is large, the thermal time constant is small, the response of the system is very swift. And vice versa. Okay, so look at the Fourier number very quickly, which is K by rho C T minus T naught LC square. T minus T naught, I'm going to call it as delta T. Okay, so this is K rho C LC square